Now, as I begin. Okay, greetings to you all. Thanks so much for joining us on this webinar of the Nigerian Society of Engineers Glasgow branch. We're always pleased to have you join us, and we always take on very topical issues monthly to help the engineering community grow in terms of education and practice and for continuous professional development. This time, this month, this very special month, we'll be looking at computational fluid dynamics, an introductory and practical industrial application session. And this is a special month to look at something like this because we just celebrated the World Engineering Day for Sustainable Development on the 4th of March. And it is about bringing engineering into applications that are sustainable to the environment, in built environment, in renewable energy, in environmental engineering applications, and so on, in ways that we're able to build the environment as engineers for the future people to use without jeopardizing their chances of using it and using it in an enjoyable way. And to address this topic in a very, very technical, I think, and impactful way is someone who is a global expert in this area. And I'll be introducing him very shortly. So for some home housekeeping before we begin, kindly keep your microphones mute throughout the session, except if you have to ask questions or you're called upon to speak. And also endeavor to put any questions you have in the chat box, just the chat tab just below on your screen there. Right, go through a quick rundown of what we have. Essentially, we'll be having welcome remarks by the chairman of the NSC Glasgow branch, and then I'll thereafter introduce the speaker who will present his talk. And then you would have the chance to ask your questions and interact with the speaker on the topic of the day. And finally, the speaker gives us the final remarks to wrap everything up. And then we have announcements and appreciation. So I hand over to the chairman of the Nigerian Society of Engineers Glasgow branch for his welcome remarks. Over to you.
Okay, good afternoon, good morning, and wherever part of the world you are, just greetings from Nigeria Society of Engineers, Glasgow in Scotland, in the UK here. Thanks for joining us today. As my colleague said, it's good to have everyone joining us just now. Just to follow all the protocol, in case if there's any technical issues while we are on the seminar or webinar today, please just drop the message, then we'll address that. And we'll make sure that we do all the housekeeping rightly. And I just want to acknowledge a few people just now before we move on to the webinar itself. And I want to recognize and acknowledge the Nigeria Society of Engineers President, Engineer Mohammed Babagana, FNSE. And also want to recognize our First Minister in Scotland, Nicola Sturgeon, and all the MPs, local MPs here in Scotland here. And they've been sort of a part of influence to our society, and they are doing one of things or the other indirectly to us, and even the partnership, all those things will be coming on as we progress it. Just keep eyes on that, and you will be seeing more of, apart from people in the engineering community, you'll be seeing more people from the political arena in our webinar in the few months to this time. So just keep eyes on our website, then you will see more on that. I also want to recognize all the executive committee, the council member of the Nigeria Society of Engineers. I want to recognize all our the branch member, the member of the Nigeria Society of Engineers Glasgow, all the chairperson of all the NSC branches here in the UK and in Nigeria. You are all recognized, sir. The fellow engineers, the associates, all the professionals, and the academicians, all the professors among us, thank you for honoring this invitation to join us today. We really appreciate you. And we don't want to spend a lot of time on the protocols. and want to just keep the time, stick to time. Sorry if I've not recognized you, I'm going to do that, and please just drop us a message. I also want to recognize our next speaker as well. You'll hear more about that, and the next speaker for the next month, Engineer Ayofi. So you are recognized as well. Thanks everyone for joining us. Hopefully we'll enjoy this webinar. If there's anything you want us to know about, please just drop message at the chat room. We'll take care of that. Over to you, Dr. Emmanuel. Thank you.
Thank you very much, Mr. Chairman, for that welcome remarks. And thanks for recognizing the presence of all the dignitaries we have in our midst. You're all very, very welcome. And I would want to continue to stand on that protocol which you've established, sir. Right, so moving on, I'll be introducing the speaker for today. I told you earlier, he's an expert in this area. He's none other but Dr. Oluyinka Bamiro. Dr. Bamiro is currently a global simulation owner. That's a technical expert for the Fuel Systems Virtual Design, Development and Validation, VDDV, at General Motors. Dr. Bamiro has 19 years of extensive professional expertise in computational mechanics, systems modeling, and experimentation, with applications in thermal systems, energy management, materials processing, multi-physics computational mechanics, cardiovascular fluidic mechanics, bioheat transfer, and automotive applications. He has authored peer-reviewed journal articles in the area of computational mechanics, and he is a licensed professional engineer in the state of Michigan, United States of America. Thank you so much for joining us, Dr. Bamiro. I now hand over to you to present your talk.
Okay, it's a pleasure. Let me know once you can see my screen.
Yes.
Okay.
Yes.
Let me go to full screen mode.
Perfect.
Yeah, you can still see it.
Yes, perfect.
Okay. Yeah, thank you very much for the introduction, and thank you for the Glasgow branch for inviting me to make this talk, and also the distinguished ladies and gentlemen, and the chairman of the Nigerian Society of Engineers, and all the dignitaries that are on this call. I appreciate you for attending, and first and foremost, I thank God, for having the opportunity to present, particularly in times like this, when we think about COVID era. We thank God for life for everyone on this call. And then I also thank the faculty members of the University of Ibadan that are on this call, and they rightly say that, for you to be great, you started from somewhere. You stand on the shoulder of giants to achieve what you are, and I appreciate them for attending, the faculty members of the University of Ibadan Mechanical Engineering. And I'll get started. And the irony of everything is that I have a long history with Glasgow. I did part of my elementary or primary school actually in Glasgow in the early 80s during my dad's doctorate at the University of Strathclyde in Glasgow there. So Glasgow is not entirely new to me. So, okay. So I'll go into my topic for today. It's computational fluid dynamics. It's an area of engineering that is vast, theoretical. As much as it's theoretical, it's also have very good applications to day-to-day things, that's particularly products that you use that you don't know, it has gone through computational fluid dynamics. So I'll briefly give an introduction and practical industrial applications, just do some mini live demo. And the major emphasis is not on the theory of it, because it's, like I mentioned earlier, it's very theoretical, and it's almost like 2 semesters of graduate level course. So I'll just skim through that introduction and then just go to applications of how it relates to us. So moving on to the next slide. Just to quickly recap what they introduced earlier on. I have a bachelor's in mechanical engineering from University of Ibadan in Nigeria, master's also in mechanical University of Toledo in Ohio, and then PhD from Western Michigan University in Michigan. I've had professional work experience in working at Whirlpool Corporation in Benin Harbor. Basically, they make appliances as a whole. You can think of dishwashers, you can think of washing machine, dryers, cook stove, refrigerators, and so on and so forth in their research and development. And I worked at Owens, Illinois in Perrysburg, Ohio. Basically, they're into glass packaging. I also worked at their research and development there. And then more recently, a couple of 4 or 5 years ago, moved into the automotive industry. I work at General Motors right now in Warren, Michigan, and product development and with regards to fuel systems, where I'm a technical expert in, mentoring engineers and, being a technical leader in the area that I'm going to talk about today. And so in terms of my technical expertise, it's in the area of computational mechanics, be it CFD, finite element analysis, fluid structural interaction, coupling CFD with finite element analysis, fatigue and durability analysis, acoustics, systems modeling, biofluid mechanics. This was an area of my PhD, looking at cardiovascular fluid mechanics within the human blood vessels, where engineering meets medicine. And then CAE simulation process, basically trying to automate your computer-aided engineering simulation workflow. Now, going to the topics for today. So basically what I'm going to talk about today, it's first of all, define what CFD, and then touch about the fundamentals of CFD, just a basic introduction, and then advantages, and then industrial applications of it. And then we talk about stages of a CFD simulation. And in the stages of a CFD simulation, I'll talk about the pre-processing, solution solving stages, and then finally the post-processing stages. And then we'll talk about common CFD tools that are used, be the commercial and open source, and then live demo of some typical examples. And then later on during the remarks stage, I'll talk about how does it, I'll defer that to under the remark stage. How does it impact me as an engineer, like the audience? How does it impact Nigeria as a nation? How does it impact engineers? How does it impact students? And I'll talk about that during the remarks stage. And then I'll defer also the Q&A, and then my contact details. So going to the next slide, basically CFD is just an acronym for computational fluid dynamics. And in essence, it's a numerical method of using computers to solve basically transport phenomenon, transport equations. And by transport equations, it can be mass, it can be energy, it can be momentum. And typically those governing equations are, what they are partial differential equations, are nonlinear in manner. And then the goal of a CFD is to discretize those PD equations in a manner that, bring it down to the level of algebra that the computer can numerically solve. So basically, to a layman, you can just say you're using CFD to solve, a complex set of equations into just an algebraic one that a computer can solve. It's nothing new about CFD. It dates back to the 50s in the United States, and when people are trying to land people in the moon and things like that. But, it gained, tremendous application over roughly the past 3 decades because of, parallel processing in computer, and then, computing as a whole, becoming cheaper. And for example, in the 40s, you can do only, let's say, 500 floating operations per second, but now you are in the area of, above 1.3 penta floating operation per second, so speed is increasing, and also the cost is, reducing. So that's what is making it, more applicable to industrial applications, not just only academic, endeavor. So going to the fundamentals of CFD and as a whole, and basically there are 2 approaches to modeling fluid models. There's what they call a molecular approach. There's what they call a continuum approach. A molecular approach, the mean free path, what they mean by mean free path is that the collision between particles, the distance between the collision between particles, that's what they mean by mean free path, is comparable to the length scale of the geometry you're interested in. And in cases like that is when you look at flows in microchannels. Like, for example, if you look at printers, most of the flows, the ink flows in microchannels. So in those cases, you most likely are going to use a molecular approach if it goes to that level, because at that level, what we call the continuum hypothesis or the continuum models breaks down. So, but just to break it down, in this talk, I'll be talking about the continuum model with regards to the Navier-Stokes equation. And the Euler equation is just a derivative of the Navier-Stokes equation. So looking at the Navier-Stokes equation here, in simple terms, you can say it's a conservation of your mass. It's a conservation of your momentum, second Newton's law, F is equal to ma, but in an elegant fashion is the second set of equation here. And the third one, you can say energy can neither be created nor destroyed, conservation of energy. You have this third partial differential equations there. And then if you want to dig deeper, you can look at your derivative with respect to time, which is transient phenomenon. And you can look at convective terms and so on and so forth. I will not dwell so much on this, but basically in any CFD simulation, this is roughly your building blocks. This is the equation relatively in its simplest form. Any type of additional physics you want to add, it's basically at times you add it as a source term, or you have multiple type of these equations and so on and so forth. But this is like your Lego building block to which we start from. And later on, I'll talk about, what additional physics or complexity you can add to these equations and when you solve them. Now, going to the typical physics, like I mentioned earlier on, with regards to trying to solve your Navier-Stokes or computational fluid dynamics, this is by no means exhaustive. There are still many underlying physics that you can capture and solve. And then later on, I'll begin to show you what does this mean? What are the practical applications, So in terms of heat transfer, it can handle conduction, convection, radiation, or either separately or all combined, all happening at the same time. And for radiation, it can be in a non-participating media and a participating media. What do I mean by participating media? A participating media it's a media that that absorbs radiation, reflects radiation, scatters radiation. An example in my previous work is when you look at glass. Glass, when you melt glass, it's at a high temperature and it's a participating media. It reflects, it scatters and so on and so forth. And then here I'm just showing, you know, different ways of modeling it depending on how optically thick those the glass is, just different approximation. And then if you could remember from our basic fluid mechanics, we have laminar, we have turbulence, you can handle that. And then under the turbulence, it can be what they call a RANS, a Reynolds average, navier-stokes. It can be LES, large eddy simulation, or can be what they call DNS. This is typically of little interest in industrial application because it's computationally expensive to do that. And as I'm showing this graph, as you move downwards like this, the complexity increases, your computational cost of solving the problem, you know, increases. And then moving on to phase, you can have a single phase, like just either gas phase or a liquid phase. And if it's just a single phase, you can have multi-species. For example, if you're modeling air, if you want to go complex and go fancy, you can have multiple species. You can have nitrogen in there as a species, oxygen, argon, and things like that when you model that. And also in there, if you want to account for chemical reaction, you can handle it with heat transfer. It's possible. And like a typical application will be combustion, like a burner, and everything is just one single phase. And if it's, let's say you're burning butane or something of that nature, it will be a single phase. And then you can go much more complex. It can be multi-phase. And under multi-phase, you can still have single or multi-species. And to give you a practical application, like in my previous work, when we model, let's say, for example, glass melting. In a glass melting, you start from sand, soda ash, and you melt it. So that's one solid phase. And then it becomes molten liquid. That's a liquid phase. And as the liquid phase interacts with the combustion space, you have gas phase, there's chemical reaction going on. So there's a lot of complex physics there with the overall intent of, you know, looking at the quality of glass melt, looking at the convection currents and things like that. And then in terms of mesh motion, what you're trying to solve, it can be stationary, it can be moving, and you can have different ways of addressing those motions that I'm showing here. You can have moving reference frames, sliding, overset, and then one is deforming mesh, whereby this is typically applicable in the area of fluid structural interaction. Let's say, for example, you are looking at an oil rig and you have waves sloshing on the platform, it deforms it. So from a structural perspective, if you're going to solve that problem, it's going to be a finite element analysis coupled with a CFD. And on the CFD mesh part of things will be deforming and then going back and forth. So in that case, it will be a deforming mesh. And then in terms of dimensions of scale, it can be 2D, it can be asymmetric, and then it can be 3-dimensional. And then in terms of compressibility, it can be incompressible, compressible. And then for compressible, it can be subsonic, it can be sonic, trying to look at shock waves, and supersonic, and so on and so forth. And then in terms of flow domain, it can be looking at internal flow, like flow in a blood vessel, flow in a pipe is internal, or you can be looking at an external flow that is flow over, let's say, an airplane, airfoil. You can be looking at flow over a car, trying to determine the drag coefficient. So that's like an example of an external flow. And then in terms of the time, you can solve a steady state solution. You're interested in the long-term perspective of the flow field, as opposed to just how things evolve with time. If you are interested in how things evolve with time, you look at a transient, what they call a transient simulation. Okay. So moving on to advantages of CFD as a whole, why CFD has a very, very good advantage over experimental methods, it allows for what I call design synthesis and optimization in a very cost-effective manner. What this means is that before you even build a single prototype, you can run through different design alternatives and optimizing the design to get either the most cost-efficient design for you before you even produce it, But if you were to do that experimentally, you have to first of all build the prototype, run the design of experiments, and then see which one is your best design. But all these ones you can do it virtually via CFD and come up with the optimum design, and even in certain cases run your design of experiments and get a response surfaces and even take it into other models and so on and so forth. And then another area that it's very useful is that if you're interested in looking at your flow field, you're trying to look at how things flow, it's very easy to visualize. And and one thing they typically say, a picture or a movie or something says more than what 1,000 words can say. So it's easily good for visualization. And then it's more recently, the advantage is even more prominent with the advent of, scientific visualization via virtual reality, whereby you can put on 3D goggles, look at your flow field, move it around, and even people looking at flow in human heart, taking a CT scan of a human heart to a mesh level, looking at flow towards in it, and visualizing it, interrogating it, and to better understand the flow field. It's very difficult to do that experimentally. And then one thing that CFD also permits, there are certain things that are difficult to simulate experimentally, either because it has hazardous, right? People look at, fire propagation, and how if something starts burning, a product starts burning, how does it propagate? How can we guide the fire to certain areas and things like that? It's a huge area of, application into fire CFD modeling. It's difficult to do that experimentally. People look at explosion, how if something explodes, how does it propagate? How can you contain it? Those kind of studies, you just can't do it. It's not easy to do it experimentally. People look at pollution. If cities are going to be polluted either because of biological agents or all sorts of things, people use that to study, pollution. Even during this era of COVID, they've used CFD to look at, how COVID particles spread. You use CFD for that and things like that. But it's difficult to use human subject experiments for all those kind of things. And also in environmental CFD modeling, wind, trying to simulate wind, tsunami, hurricanes, and its impacts on society, and how you can build structures and levees and things like even wind-induced vibration and things like that, subsea structures. And then for certain large-scale structures, it's just not practical to just build and build and build like airplanes. It's very used in the aerospace industry, ships, naval engineering and things like that. And so that gives you advantages of it. And then here I'll just give some typical industrial application with that, and by no means is it exhaustive. The application is wide. So I'll just go through some of it. One, in the automotive industry, people use it for drag coefficient, just to see, and as your drag coefficient affects your fuel economy and things like that. People look at it for cabin comfort, how the HVAC, once you put on the AC, how does it spread uniformly within the comfort of your car? People look at engine combustion under the whole thermal management of your car to make sure everything is at right temperature and things like that. And in aerospace, almost similar to the automotive industry, drag and lift, airflow design, cabin comfort. And then in biomedical service industry, they use it, for all sorts of biomedical devices. As long as fluid flows through them, it can be simulated to optimize that design in flows in in blood vessels, the heart, and so on and so forth. And then in power and energy, turbine design, cooling towers, combustion, burner design, etc. Oil and gas, they can look at, free structural interaction, or like I mentioned earlier on, of the oil rig due to either wave induced or wind induced loading on it by the sloshing of the waves, and then also for oils, designing separators, pumps, valves, etc. And then from the civil engineering perspective, or even architectural engineering, you can look at it, within a building, HVAC, you can look at it for air quality assessments. There's one I'm working on that has to look at, looking at the quality of air within a room, and even more recently in the era of COVID, people simulating when people either sneeze within a room, how long does it take for that particle or the virus induced into the room, how long does it take to leave the room? And so that people can design HVAC efficiently. People look at it, pipeline systems, river engineering, coastal and wave modeling, and things like that. Electrical engineering, people are, if you have data centers, you're more worried about electronics cooling and so on. And in chemical engineering, reactor design, material processing. When I worked in the glass industry, we use it heavily, for either the furnace design and for having good uniform glass temperature and all sorts of things. And this by no means exhaustive, So then moving on to the stages of a CFD simulation. And basically, like I mentioned earlier on, there's what they call a pre-processing stage. Basically, you are trying to clean up. Somebody's going to give you a card. Let's say, for example, on the car here, on one of the demos that I'll show, like they give you like in 1964, I think this is an Aston Martin DB5. And they want to calculate the drag coefficient on it, So basically, once you're given this geometry, and most geometries of industrial relevance are usually complex. And from a CFD analyst point of view, we always say it's not watertight. Typically, if you are trying to solve something, particularly for internal flows, you want to make sure it doesn't leak, that it's watertight. So you go through the process of trying to clean up the geometry. And in terms of the CFD analyst time, most of your time is spent at this stage trying to get it ready to be simulation ready. And then the geometry, the CAD geometry, you can receive it in native format, like if you work with SolidWorks, NX, CATIA, Autodesk, it can be in their native format. And then it can be in a neutral format, like STEP, IGS, Parasolid, or in tessellated formats, and so on and so forth. So once you're done with that geometry cleanup, what you are interested next is to divide it into what we call computational cells or control volume for the computer to solve. And like in this example, all this, but the external geometry of the car shown here, you are assuming it's in a wind tunnel You divide it into several cells. So that's what the meshing involves. And that's what they typically talk about cells. And the cell count typically affects your computational cost and accuracy. The more number of cells you have, the more accurate your solution is going to be. But it's also at the expense of your computational time. And time means, in terms of CFD, time means dollars, time means naira, that means pounds, sterling, or whatever. It's so for us as CFD analysts, what you try and balance is the computational cost and the level of accuracy you're willing to take, and to be able to make value-added decisions. So, and then more also important, it's how you distribute those cells. You know, you want cells to be located where there is high gradient in the solution field, and lower cell count in areas where there are lower gradients, or you are less interested in certain phenomenon. Like, say, for example, if you're looking at this car here, because I'm interested in calculating what they call the drag coefficient, and it's a surface phenomenon. So if you look here, the cells are more clustered in this region here than over here, That's because in calculating the drag, I need a high level of refinement here. So that's the distribution of those cells are not uniform. And then the next stage in the pre-processing stage is what we call the model setup. Like I showed you earlier on, determining what physics do I want to simulate, right? Like in this case, first of all, this is going to be an external airflow. Is going to be, I'm assuming it's going to be incompressible, and it's going to be a steady state solution and things like that. You start making those assumptions, and then you solve your solution. And then one other thing is also, what discretization schemes am I going to use? And that definitely determines your order of accuracy. Is the first order, is the second order, is the third, fourth order, and so on and so forth. And then also from the setup point of view, you talk about your convergence tolerance. How much tolerance do I say, okay, enough is enough. I believe this is an accurate solution. Either you can stop the solution or move on to the next time step. So you have to define that. And in certain cases, you look at certain metrics, not just only the numerical tolerance to say, okay, I think this is good enough. And then you look at the, if you're going to do parallel processing, either sending it to a supercomputer, or in certain cases, running it on your laptop, depending on how complex it is. You determine the number of CPU processors to use at this stage. So this one is more heavily involved in terms of the CFD, in terms of the analyst's time. That's where most of the labor cost might go, trying to get the geometry ready. Then moving on to the solution stage is just pretty much simple. Just submit the job to your compute server, on which you're going to run the job on. And usually in most industrial application, you typically use parallel processing, use supercomputers, or more recently, people have started using what they call GPU, graphics processing units, to speed up the simulation. And then here, the analyst time is barely minimal there, but where most of the cost is induced at this stage is basically your infrastructure cost, in terms of, do you rent a compute server, or do you have an in-house compute server, or things like that. That's where most of the cost is, more infrastructural cost. And then the post-processing stage, typically involves, there is analyzing the results that you've generated, into some meaningful data sets, and in which you make, a value-based engineering decision. And we typically don't just run CFD analysis for running sake. You want to answer questions, from an industrial perspective of things, and usually to either to design safer products or to have cost-effective products. And like we engineers, we solve problems. So CFD in itself is trying to solve a problem, answer a question. And so that's why I always talk about value-based engineering. It must bring value in terms of the product delivery or in terms of costs, or one way. That's at the end of the day. And then typically this involves, generating contour plots, animation movies, graphs, and reports. And like I mentioned earlier on, the trying to make those solid value-based decisions based on your analysis, involves your good engineering judgment by the analysts. And that comes by virtue of your background in the field and also experience over time. As you gather more cases to solve, you gather that experience and solve it. Then moving on to, most softwares that are available, to do this, both from a commercial and an open source perspective. And so like I mentioned earlier on, we have preprocessors that use to clean up the geometry. You have solvers, and then you have post-processor to view your results. The ones shown in green are what they call open source versions that are just freely available for anyone to download and use. And the ones shown in yellow are the ones that are commercially available. You pay for them to use them. And the ones over here at the bottom here are what they call integrated work stream. They have all the pre-processing, the solution processing, and the post-processing all in one. And most of them are usually typically commercial applications. So for commercial applications, they are more of like a black box. You don't know what's going on inside. You don't see the source code. You don't see anything. But they have very fancy and graphical user interface that you can use to set up. A lot of R&D dollars has gone into that, and they charge a huge amount of money for them. But more recently, there have been some game changers, at least on the solver side, like OpenFOAM. That's what I'll be showing today. And that's why I see value and potential for people adopting it, particularly in developing world, in cases like Nigeria, where the cost of ownership of some of this is very expensive. But they have solvers that are good enough that can do what this does. But the only downside of open source is that the learning curve is very, very steep. It takes a long while to get a handle of things, for open source versions. But once you get a handle of things, it's a very cost-effective solution, and particularly for people thinking about the financial part of things. And in my career, I've used a couple of them. I've used Answer, I've used Hypermesh, I've used FreeCAD, Salome, OpenFOAM, almost everything here. And then the two prominent ones among these that I've used is the Fluent from ANSYS, Siemens Star CCM, the two major hitters there. And okay, then moving on. Okay, so I'll just quickly run through what I intend in doing a live demo of. And the first one, it's a valve. And so typically for valves, what people are interested in is you're looking at, pressure drop in a valve. And either, typically for those valves, people run pressure drop analysis to see, okay, what's going to be my pressure drop at a certain flow rate, and you get a system curve. Either you put it into a pipeline system model, or it drives the cost of the pumps you are going to use. So you can run some of this analysis like this, and at different valve opening positions and so on and so forth. That's one I'm going to show. And then moving on to the second one is just an example of a Volkswagen bus here that, I calculated the drag coefficients, and also similarly for an Aston Martin, looking at the drag coefficient and comparing it to that of a Volkswagen bus, and then the other one here, it has to do with, it's a transient simulation. It shows a bottle filling, and typically in a bottling plant, like I always say, time typically means dollars, time means money. And you want to fill the bottle as fast as you can without, having the whatever you're filling, coming out. And so you're looking at a 1 second fill rate, looking at a 6 second fill rate, and then looking at the amount of backflow you have and things like that. So I'll show that, and then I think that should be it. And okay. Hello, am I still on track?
Yes.
Very much.
Yes,
Yeah, go
yes,
on.
yeah.
Okay. So like I mentioned earlier on,
Please go on.
okay, like I mentioned earlier on, this is a case whereby, you are looking at a valve, and then you are interested in determining, as you solve iteratively, what's going to be your pressure drop. And in typical applications, to start out with, you are typically given the geometry. Let's say, for example, if I load, let me open. Let me open something like, and by the way, for this case, I was using OpenForm. It's an open source, it's freely available. And so let me open. So in this case, created the geometry. It's in, like I mentioned earlier on, is in an STL format. And then I'm loading. Let me load it in just to show you the geometry. Yeah. So this shows the valve. Typically, you are more, let me switch off the extended walls. Okay. Yeah, you are usually interested in, you are given a valve like this, and I think the flow direction is from my right to my left, and let me reduce the opacity here, and the flow is gonna go, in here, depending on the valve position. You are going to have different level of restriction. So you can typically, in this case, generate your pressure drop curve for different valve opening positions. But I think this one was at a 15 mm from the seats here, and then you look at that, and then when you're trying to solve something like this, and like how you would normally do it experimentally, you're going to have what they call an entrance length. You're going to extend it, you have your flow coming here. You just don't start the flow here because you want it to be fully developed, like how it would be, let's say, for example, in an oil pipeline or whatever that it's flowing through. So you extend, in this case, I extended the domain upstream of it, and then downstream of it, and then I look at in my analysis here, I look at what I call the total pressure here, the total pressure downstream. You surface average it, surface average the total pressure here, and do the difference will give you your pressure drop at different flow rates. And by the total pressure, I mean both the static pressure, the hydrodynamic pressure, and also the pressure due to height changes. So in that case, so after that, you submit, you mesh it. So if I show you an example of how a mesh will look like, let me disconnect this and okay, let me see whether I have a state saved. Okay, I don't think I have a state saved. So okay. Okay. Just a minute. So let me like okay. Go on here. Just trying to load the mesh. Yep. So after doing that geometry, this is what your typical mesh will be. Discretizing it into cells that I mentioned earlier on, and then typically the way it goes is that you are interested in the regions that interfaces with the liquid. So as is shown here, it shows, regions that are actually in contact with fluid region. And then if I take a section cut of the mesh and just a minute. So my Z normal. And then this kind of gives you a section cut of that, and then you can kind of have an idea of how the mesh looks like and things like that. And once you take a section cut and things like that. So that gives you an idea of how, the meshing looks like and how the meshing operation. And then when you go to the result phase, what I'm looking at here is looking at, streamlines, how the flow goes under the seat here, and showing, because of the gap here, you have high velocity regions coming up and going there. And on the right here shows, a section cut at mid-plane, showing your flow in the valve, and it's gonna come. It's not shown here, but it's cut such a way that you won't see it. It goes. Sorry, it comes. I think it's flipped around this way. It comes this way and then goes underneath and then goes out. And then here is what I look at my pressure drop. And typically, you can use this as a convergence criteria. You run it long enough that you feel it's stabilized, and then you can, take your pressure drop over there as the solver iteration continues. And then this is a very huge amount of pressure drop because there's a huge amount of flow going there. And then similarly, without being redundant, this shows for, I think the initial one I was showing was roughly 20 meters per second flow velocity going in from the inlet, and now I reduced it to 10 meters per second. And then you see, if you look at the pressure drop, it's like 1600 compared to my initial one, which was 6500. And here, if if you look at it, I reduce it to 5 meters per second. You see the pressure drop is, way much lower. So definitely, as you expect, from a physical and intuitive point of view, the more flow rate you put through, the more your pressure drop, the more it's going to, from a practical aspect of things, the more it's going to cost you in terms of the type of pump you are going to use that will be able to overcome that pressure drop. So that's, if you look at it in terms of pipeline engineering, that's how, you come up at times with sizing of pumps, or is there a way that we can better optimize this valve so that we can get a certain flow rate for that design. Those are kind of design considerations you take into cognizance when you do things like that. Then moving on to the next one that I'll talk about has to do with, let's say, for example, looking at a bus like this. And why drag coefficient? Because drag coefficient typically affects your fuel consumption. And so typically you set up a model like this. Let me show you what you typically get. What you typically get, maybe you get a geometry. Let me go to my constant. You get a geometry like this, and then while it loads, okay. So here you get a geometry like the bus, or it can be any car of interest that you're trying to do, and this by no means is limited to just cars only. For example, even in sports, people look at design of golf balls is basically the same principle. People look at swimmers, when people design swimsuits and all those other things, it's still the same underlying physics. You're trying to calculate drag coefficient there. The application is limited in certain cases by your imagination, so there's a lot of areas you can apply there. So, but for the context I'm presenting here, is you're looking at a bus and you're trying to calculate the drag on it. And typically what you do, the bus is moving at a certain speed. So from a CFD perspective of things, you just don't move it at that. You can try and move it at that a corresponding speed, but you still get the same results. So like keeping it still and then assuming there's a flow going over it. And so that's what I've typically done here. And in most applications, you put it in what they call a wind tunnel, and then you send in flow at a circular speed and then calculate the drag coefficient. Basically, that drag coefficient at the end of the day relates to the friction force, and that is lost, affects gas mileage and so on and other forth. And then in terms of physics, it's just an external airflow. And if you're interested in internal airflow, there are cases whereby you are looking at the cabin comfort within the car. You can look at that like I mentioned earlier on. So this shows you the geometry. I have a wind tunnel and so on and so forth. And then you follow the same procedure like I mentioned earlier on. At the end of the day, mesh it, look at the mesh. Like I showed in my presentation here, just a minute. When you look at the mesh here, this region here is well refined, distributed. And then as I move further out, the distribution reduces, And at the end of the day, you look at the drag coefficient on the higher the drag coefficient, the more friction forces are, the more the gas mileage will be. So looking at for example, this bus, the drag coefficient is roughly around, the drag coefficient is roughly around 0.48. And if you compare that to, let's say, the sports car that I was showing, like the Aston Martin, the drag coefficient for that was roughly around 0.29. So you can see, because the body of the Aston Martin is, is shaped, that there is, less drag, it's contoured, it's streamlined, and then, it leads to less drag, as opposed to when you compare it to something like this, right? Where you have a lot of surface area for the flow to hit, a lot of drag, and then we can look at things like, streamlines, how the flow is, the recirculating line, and all sorts of things you can do. And then moving on to one more application, it's this, like I mentioned earlier on. The application here is let's say in a bottling plant, and they want to see how fast can they fill, because the how fast you can fill determines your job rates and how much bottles you can fill. The faster you can fill, the more cost efficient you are. And so basically you're trying to push the limit. So can I fill this bottle? It's like a wine bottle. Can I fill it within a second? If I can't fill it in a second, can I fill it in 2? Can I fill it in 3? And so in this, you look at, different designs, like when I started with this, look at different design. You can look at even different designs of these nozzles. You can, all sorts of things that you can do with that. So, and on this axis here, we show you, how much backflow you have in terms of how much of it is going out in total as you fill. And then here is just the blue shows you the flow rate, the instantaneous flow rate. And there are different applications of this in different industries, not just only limited to bottle filling at the end of the day. So in this bottle filling example, if I show you the animation here, so this on the left-hand side here is they're trying to fill as fast as they can. They're trying to fill this. This is roughly around 740 ml, trying to fill it within 1 second. And as you can see here, once you start filling, because of the air entrainment, it circulates up, and then everything spills out, like almost 1.2 mils within a very short period of time. And if you try and reduce the fill rate in this case to roughly 6 seconds, and then shows you a normal fill rate, it's filling normally, even up to 0.5 seconds, and still no backflow. And this basically can drive a lot of solution strategies. And like even for this case, you're assuming a constant fill rate. You can do a control system whereby you use variable fill rates. Maybe once the level is here, you fill at a certain flow rate. As it's coming up, you reduce your flow rate. So all the kind of design decisions that you can make based on the power of trying to use CFD. And then one more area just before I go back to the presentation that I just want to share. Let me disconnect this. It's in the area of HVAC design, and So this one typically shows you what people can do in terms of, HVAC design. You take, for example, you are in a room. This one, I don't have the results yet, but I'm working on that. Wherever you're in a room, you are trying to design a central air conditioning system. This is just for a typical room. You can scale it up to the level of looking at a whole building, looking at airflow patterns, which areas are dead zones, what area doesn't temperature heat uniformly. And within this landscape of this room, you can look at a typical US sized room. I think it's 300 square foot by 300. And then if you look at it, there's typically in the States, they have a register that is tiny here, whereby you introduce your airflow field. And then you have your return register is going to be somewhere here. So if you look at it, the flow comes, typically is a louvered blade, is going to go this way, and then go out that way. And then you look at the flow patterns. There are metrics that you look at, like the mean age of air in the room, how long does the air stay there? And then more recently, people look at particle modeling, like for example, you have an human model here. And then if you zoom in, you can release, particles from the nose or from everywhere. And then just to simulate, for example, in this era of COVID, that how long does it take for those particles to stay in this room? Assuming, your HVAC is working and you're sucking out air out of that room, how long does it take those particles to stay? If you have 2-3 individuals here, how long does it take? And what does that practically mean for you as an engineer? You can now begin to look at, where can you optimize those those registers, inlet registers, outlet registers, how much flow should you put in, and things like that. A lot of areas that people are exploring and trying to look at things like this, and so just to spark people's interest and imagination. So, and then going back to my presentation, so I will defer the question and answer to under the remarks question, and then in my closing remarks, and then these are my contact details. If you're interested in, just, for consulting, training, or, collaboration for academic research needs and so on and so forth. That's my LinkedIn page, and then email cifasolutionllc@gmail.com. You can reach me. So I yield the floor to you, Ima.
Thank you very, very much, Dr. Bamiro, for this exceptional presentation. I think you have taken us through something that is like a crash course, a practicum, a lecture, all wrapped in one, and bang on time, very spot on, encompassing practical applications. You've ignited the interest of very many of us, and given project and research ideas to so many other people, and so on. I mean, this I find is very insightful, very engaging, and educational, informative. For me, this is a very great one, and I think everyone shares my sentiments. We would have done a very thunderous round of applause, but I don't know how we'll do that virtually. But just to appreciate the presentation, thank you so much for this.
Yeah.
Thanks a lot, Michael, Wave, and others for the applause there. This is a great presentation.
Yeah, thank you.
I see there is so much interactions and engagement in the chats, and I think lots of other people would have questions to ask as you've envisaged. So I'll be handing over now to my colleague who will be handling and managing the Q&A session, Engineer Charles Ngwacha from our technical secretariat. Engineer Sharp Ngwacha. Engineer Sharp, please.
Thank you very much. I think we can, without overflogging the issue, I think we can just put a round of applause to Dr. Yinka. Let's do that. I mean, Okay, thank you very much. So I've got some comments. I've got a hand up already. Who has a question to, please, if you may, mute yourself. Once again, I think we're done with the clapping. We're going to take hands that are raised. We're also going to take chat questions that are put in the chat room, and we will see how we go with time. Please, I will advise that you will be straight to the point with your questions and consider others, because I think everyone wants to get their own question across. So first on the hand has been up for some time now. So let's hear from Michael Obeifun. Michael, after Michael, Dr. Adeaga, get ready. And after Dr. Adeaga, we take a question from Tuoyo. And after Tuoyo, we take a question from Fen Chris. So in that order, Michael, Dr. Adeaga, Tuoyo, and Fen Chris. And we, after that, after this four, we'll take some typed questions from the room. Michael.
Okay, thank you very much, Yinka. That was very lovely, and I really appreciate that. I have two quick questions for you. You talked about the advantages and the wide application of CFD in industry and even in research. I really appreciate that. But you didn't say anything about the demerit. I don't know if I missed that. I want you to comment on that. And secondly, I want you to, because for example, in my research, I'm dealing with a large scale system, like in deep water. You're talking about a system in deep water, mooring system. You know, these systems are very large. Okay. If we want to apply CFD in solving this kind of problem, how do we deal with the scale problem? These are the two questions I have. Thank you very much once more. Yeah.
Okay. So in terms of demerits, right? The demerits that I would typically think of is the training it requires, right, to come to use CFD analysts and things like that, right? I would think about in terms of that demerit from an industrial perspective, right, compared to experimental methods. Experimental methods, to a lesser extent, when you run them, you don't need a certain level of training to do it, right? But for this, definitely you require a certain level of training. That's one. And then secondly, to get to this level whereby you can trust CFD simulation in an organization, there's an evolving process, right? That you have to make sure you are using the best practices, right? That comes by painful years of development and even what I call virtual experimentation, that to get to that level of expertise, which industries don't typically share, right? It's just, okay, CFD, you can get this advantage and so on and so forth. But to get to that level of experimentation, that level of expertise whereby you can replace, in certain cases, experiments, right? It's a painful process, right? It takes time. It takes dollars, it takes everything to get to that level. But at the long run, it pays off, right? But during that process, you can look at this as a disadvantage, right? Because you can easily run an experiment at times, right? When you're going through that learning curve, right? But on the long run, it does pay. So I can look at that disadvantage during that, that learning process, right? And then also one other thing is that you also need initial infrastructure to do some of those things, right? Although you can't compare some of the initial infrastructure to running experimentation, but it's still there. It's still there. So now going back to your question of, large scale problem, it's when you solve large scale problems, you also face the same problem in experimentation, right? What you can do in that case is to reduce the problem to, much smaller scale problem. What do I mean by much smaller problem? As we know in fluid mechanics, right, where it's what we call the dynamic similaritude, whereby you look at your dimensionless numbers, you reduce your problem to a scale that it can be governed by certain dimensionless numbers, and then you can now simulate at those levels, right, you can scale it down to something that is manageable computationally. For example, you are looking at free surface flow. You have dimensionless numbers like your Froude number and so forth, that you can reduce the problem you are trying to solve so that they have similar Froude numbers. If you're even solving problems that has to do with Reynolds number, get it to a certain level that, you know, the Reynolds number are identically similar if you are dealing with very large scale problems. Or look at, if you are looking at surface tension driven flows, look at the Weber numbers and etc. etc. That's one approach I would look at, you know, trying to look at large scale problems like that, you know. And if you have some people, if you have their compute facilities, then they can run how big it is. And then depending on what you're trying to solve also, at times some crude model is good enough, depending on what answer what question you're trying to answer, right? And that can also dictate, you know, how much level of fidelity your model needs. And hope I answered your question properly.
Yinka, thank you very much. I'm grateful.
Yeah.
God bless.
Yeah.
Thank you very much. Dr. Daga.
Thank you very much, presenter.
Brief, sir.
Now, you have done justice to the presentation, and I really appreciate it. Kudos to your knowledge. Now, then my first question goes thus. Does CFD requires writing codes from the scratch? Now, if it does, then what type of code do you think is essential or that is very important to handle CFD? That is question number one. Now, question number two. Now, studying most of these platforms for simulation, it seems that most of them are biased towards finite element methods. And of course, we have many numerical methods.
Yeah.
What makes finite elements more important than possibly others? Because I actually use this vortex element method. That's what I use.
Okay.
Question number three. Now, all these open form, ANSYS, Fluent, and the rest, do they essentially give the same results if they are well programmed? Thank you.
Okay, hopefully I remember all of them. Okay, so like you mentioned earlier on that, do you have to do coding? The answer is yes, and I will say yes and no, depending on what you are doing and what you are after. Like when I did my PhD, I did coding myself using you know what I mentioned earlier on, the molecular methods using lattice Boltzmann. I did a lot of the coding myself, you know, using things like Fortran and so on and so forth, right? But to be realistic, when you come to academic and to industrial environments, you will most likely do very little coding, except you have very niche applications. There are certain applications that what I've presented here are mainly general CFD codes, right? And there are certain niche applications whereby it's very niche, then you might go to the territory of trying to program. Or at times, maybe there are certain things the general CFD code doesn't have, right? And that you want to add functionality to it, then you might code, right? You might add either user-defined functions if you're using ANSYS and some other ones. But for something like OpenFOAM, if you are doing academic research, the code is there for you. If you want to add additional physics that is not already inside the underlying code base, you can do it. You know, you can definitely program. I think the one I showed today, it's called OpenFOAM, and it's based on C++. And then you can add more code as more code you want to do. But in most cases, most of the stuff you need, you know, for for industrial scale problems, it's already in there. But if you want to extend it beyond, definitely you can use C++. And now talking about, you know, talking about what discretization schemes they use. Even though I did not mention it there are a couple of ones people use. But within the CFD context, the most popular is what they call the control finite volume methods. It's the most common. Actually, finite element methods is used, but it's not very common in CFD applications. Is mainly using finite volume methods. Nevertheless, there are other methods. People use SPH. You talked about vortex element modeling. People use spectral methods, etc. Right? But the most widely used is the finite volume method within the CFD context. Reason being that it's because of its strong conservation form. When you look at it mathematically, it's very conservative, and that's why people use it. As opposed to, if you look at finite element methods in fluids, people do use them, but it's not as in its very conservative form as finite volume based method. Finite element method is mainly used in when you go into the structural space, but within the fluid space, it's rarely used. I actually know of only one code that actually uses it, the Altair Accusolve. So, but it's to say which methods is the best, it depends on application. But as a general one, I would say finite volume methods is usually the most widely used, and hopefully that answers your question.
Yes, you have done justice to them. I'm very grateful. Thank you.
Thank you.
Thank you. So the next question, let's take Toyo, please, quickly, and maybe we'll take Toyo's question and at the same time as Chris' question together so that we can have I'll note them down and we don't have to save time.
All right, thanks, Sharp. Thanks, Sharp. Hi, Yinka.
Hey, Toyo.
Good to hear. Yeah. Yeah, just two questions really. I was hoping to get your help with. I think again, from an engineering perspective, the big problem is application. Obviously, to get recommendations that will be practical or pragmatic for use. But one problem I consistently see with CFDs, and I was hoping maybe you could throw some light on this, with regards to validation of some of the tools out there. I think the gentleman a bit touched upon it earlier, because of course you cannot do large scale, field testing for some of these things. For example, explosion simulations or fire and gas, which is what I come across most times. So of course you struggle to validate. So that's the first question. How do you do that? Then second question is, I know you didn't dwell much on, you mentioned your molecular model with the statistical approach. That's something, maybe you could dwell a bit on that, because it's something that seems to be rearing up its ugly head again and again, especially with like stochastics, non-deterministic approaches, variability in parameters that you need to model along with CFD.
Okay. So in terms of validation, right, based on my industrial experience, it's it's a huge endeavor trying to validate. Now, validation comes in different stages, right? It depends on, at times, there's what we call A to B comparison, right? That's the easiest one you can do. You're trying to look at a design A versus design B, which one is better, right? CFD it's very easy for CFD to do that, right? You're not looking for absolute, absolute performance, right? So there's little to much validation. Yeah, people do validation, but it's matured. You can easily do that. Now, the one that you talked about, if you want absolute validation, like you, I think you are elucidating too, in that case, it comes by, you have to invest money in trying to do that, right? In terms of, for example, in the industry, you have test cases, areas you are interested in, you have experiments that you can benchmark with, right? And then you run all those test cases and see how does the code perform. That's how you look at it. And if the code does not perform, you begin from an analyst perspective of things. What are the things that are lacking? And what did I model the physics correctly? Is it a mesh problem and things like that? It's a whole kind of pseudo academic exercise on its own, to make sure you validate those models, right, with experimental data. I do that day in, day out at work. You have this test case. You just don't jump the gun and say, okay, yeah, we can simulate it. First of all, you make sure you validate it. That the first thing we ask them, do you have an experimental model that you've run in time past that we can validate? Twofold, it gives you as an analyst a level of confidence in the work you're doing. And two, the person you are presenting the results to, it gives them a level of confidence too. So you have to definitely invest in validation. And then one other advantage of that, once you have the physics or the area of interest that you have that is validated, is helpful too at times when you switch codes, right? You go from one code to another, then you look at it, okay, let's validate it. Let's see how good that code is relative to the previous code that we have. That's one area, based on my experience, that we've approached validation. We always take every CFD result with a grain of salt. First of all, you say, okay, you give it a test case that that you have experimental data to, and then you validate it based on that. And then you can now gradually, build over time. As long as the physics that governs that domain that is validated doesn't change to a lesser extent, you have a level of confidence. If it changes a little bit, then you might take it with some suspect that, okay, maybe we need more physical testing to correlate and so on and so forth. And then moving on to your question of there are two folds there, talking about stochastic and also talking about variation. There are ways to account for variation, but it's usually typically, if you want to look at it from the context of the continuum model, it's expensive. You're looking at, let's say, for example, I can just give an example of the bottle filling that I'm showing. There can be variation in the material properties. There can be variation in the flow rates in reality in the industry, in the plant. There can be variation in the diameter and things like that. There are areas whereby people run variation as a study to look at, even using Monte Carlo methods with CFD to look at, interrogate the space, how much variation you're going to have, and simulate it, and to get kind of like a response surface of your performance, subject to more realistic manufacturing variation. But the caveat there is that it's very expensive to do that. It's very, very expensive to do that, and it's after some time it becomes more of an art, that how can you balance your accuracy with the amount of variation you want to get, depending on the scale of the problem. Then in terms of stochastic methods that you mentioned, let me go, the stochastic methods you mentioned here, it depends on, I would say, the kind of problem you are trying to solve. If it's variation, then you can use Navier-Stokes equation and things like that. But if your problem becomes a length scale problem, and then definitely statistical methods is the way to go. Like, part of my PhD research was in this area of lattice Boltzmann, and whereby you can recover to a lesser extent whether you are solving flows that are discontinuous to flow that are continuum, then you can use the Boltzmann equation. And there are some codes that are out there that uses the Boltzmann approach. Actually, one of it is power flow. But the caveat there is that because of the nature of the way the equations are, it's transient. What I mean by transient is that you have to evolve with time. And in terms of computational expense, it's very, very expensive, but people do use it, but they use it to interrogate systems and then maybe scale it up to using it on a Navier-Stokes equation. For example, flow in porous media in the oil and gas area, people use lattice Boltzmann when you have structures that are, you easily can simulate with this, park beds and all sorts of things, right? You can use that, but you have to find a way of scaling it up so that it becomes of practical application because it's expensive. It's an expensive route to go. But if your area of interest is just for a very short transient simulation and everything, people do use them. Hopefully I addressed your question.
Okay,
Thanks,
thank you
Inka.
very much.
Thanks so much.
Yeah.
Thank you. Let's have Chris. Please, let's keep it brief. I know he's trying to be elaborate with the answers. I don't know how many more questions we can take. Fen.
Yeah, thank you. Good evening.
Good evening.
Okay, mine is not really a question though. It's something I've done with a SAC software, and offshore wind energy. I don't know. You talked about the when you started with the advantages. You talked about the ability of the CFD to do analysis in structures too.
Yeah.
So I want to ask, first of all, how can one export a model from SACS to say something like ANSYS or that open form? And then secondly, what and what do we need if we really want to analyze offshore structures? I don't know if you get my question.
Yeah, repeat the last question again so that I get it properly.
Okay, I said what and what do we need, like in terms of analyzing offshore structures? What kind of analysis would you advise we use maybe to run it?
Okay. So in terms of exporting model from the software you mentioned, I've never used it before, so I really can't talk, what you're going to export or whatever. But I'll talk at it from a general and a physics point of view. Let's say, for example, if you want to, what you're talking about is what they call fluid structural interaction, FSI. And what you need, if you're looking at an oil structure, right, and is the wave is, let's say, for example, sloshing, right? Typically in that case, what you map, some people talk about mapping, right? What you map onto the fluid structure is going to be your pressure loading, right? And the pressure loading goes into your fluid structure. Your fluid structure is going to deform, right? Once your fluid structure deforms, right? What the fluid structure is going to send back into the fluid solver is going to be your displacement and your velocity. Now, the displacement and the velocity goes back to what I talked about here. You see your domain here is deforming now. So your domain at this instant in time is going to deform, right? And then you have to remesh a little bit and then continue solving your CFD. And then the CFD, again, based on the deformed mesh, will deform, and then you solve the flow field, you map the flow field back, and it goes back and forth like that. And in that context, that's what they call a fluid structural interaction that is a two-way coupling. That means the deformation of the structure at times affects the flow field, right? And you go back and forth, right? So that's a two-way coupling. And there are certain cases that you try just a one-way coupling, right? Maybe just the fluid pressure, you just map it to the structural solver and solve it once. You don't go back and forth. But the going back and forth is very accurate, but expensive, right? Because first of all, you are solving a transient problem. And then secondly, your mesh is deforming. You have to be remeshing and then back and forth like that. People do it. I've had applications where I've done that before, and it's part of my PhD. I looked at that too. So there are cases whereby you look at that, but there are cases whereby it's just a one-way coupling that is good. For example, when you look at sloshing in a tank and you are hitting the walls, right? Depending on how rigid those walls are, it doesn't deform that much. If it doesn't deform that much and you're interested in noise, then in that case, a one-way coupling, just map the pressure field and then solve the noise that is generated based on the vibration of the structure, because the displacement of the structure itself is very minimal relative to the flow, disturbing the flow field. So it depends on what you're interested in, but definitely for structures and oil platform and everything, it has to be a two-way to a lesser extent. But if you want to go one way, it's possible. But so hopefully that addresses your question.
Yeah, thank you.
Yeah.
Thank you very much. Now, I will soon contact the team and find out how many more minutes we have. But let me just read out 5 quick questions here. I think they're just going to be kind of one line or one sentence answers. Is there a platform for beginners to learn CFDs? I mean, a CFD platform for beginners. That's first question. Number 2 question is, generally speaking, how close are CFD results to experimental results? How close, generally speaking? I think that's too wide to talk.
Yes.
And then number 3 is, can CFD predict or call out cavitation issues in pumps? And I guess, or erosions also, cavitation and erosion. And then number 4, can CFD select pump types or be used to select pump types? I guess that's what that is meant to be. And then finally, for Nigeria, I have a question myself, but I'll let others go first. CFD labs, are there CFD labs or centers in Nigeria?
Okay, I like that last question. Is one of my closing remarks. Okay, like for how applicable it is to Nigeria. Okay, yeah. So the
platforms for CFD beginners.
Okay, platform for CFD beginners, resources that you can go to. And I think there is a resource that is called CFD Online. If I'm not mistaken, I think it's cfdonline.com. You can use that as a platform. And there are many forums that you can go to. And then one software I will tell you to go to in terms of the solver is OpenFOAM. It's free. You just got to spend the time and the painful hours trying to get to know it, but it's free. That's for sure. And then moving on to cavitation in pump. People have used it for cavitation in pumps, but I've never tried it. It's not my domain of expertise, but people have used it. And then I can tell you, yeah, it can to a lesser extent, but you need to talk to experts in that field. And then cavitation of pumps and wear and things like that, I believe you can. But you might need some surrogates. It's not going to tell you exactly erosion. Basically, what you might use, maybe like the pressure or whatever loading or high pressure or peak pressure. Then you have to have like another surrogate model that you can correlate between if this pressure is generated here, what does it mean in terms of erosion? That's where you can look at things like fatigue and durability. How many cycles of that amount of pressure loading will lead to wear, right? Now that's where your experimentation comes into place in terms of the material. You must have run several experiments that you know that if you have this setting of pressure, it can withstand it for this number of wear cycles and things like that. So that's where you have cross collaboration between your experiments, your material testing, your CFD, blah, 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 and so on and so forth. And then can it be used to select pump? I can say yes or no. I can definitely say yes or no in the sense that you run CFD analysis to answer questions, to look at what's the pressure drop within the system, which will eventually aid the engineer in selecting the pump, right? In looking at your transmission or your losses and things like that, getting a system pressure drop and then determining is my pump capable of delivering this, right? And at times you might not necessarily have to use CFD for that. At times it might be just hand calculation, depending on how complex the system is. There are cases whereby I've done system models that you don't have to go to the level of fidelity of CFD model. It might be 1D models using very basic equations and things like that. And then you can come up with that. It depends on the complexity of the problem at hand. And then talking about, are there CFD labs in Nigeria? To the best of my knowledge, I don't know. I don't think there are. So over the course of my career and starting in this area and then maturing, and now, mentoring young engineers and mentoring engineers all over the world, I've had cause to collaborate with people in North America, US, Mexico, South America, Brazil, and so on and so forth in Asia with Korea, India, China, in Europe, Italy, Germany, all over. And I've happened to also, particularly Asian countries, to collaborate with them that they're in the same stage of development. They can see they're developing like Nigeria, right? And you have developed countries that they outsource some of their designs, right, to those countries, right? And the reason they do some of those things is because there is the human capital available that is trained, right, to deliver, those results, right? They have that expertise, right, to deliver. That's why value-based engineering, like I mentioned earlier on, we always go to a place that is like water flow from the high to the low, right? If the cost is cheaper somewhere in developing countries, as long as the expertise is there, it will flow there. And that's why you see some of this CFD work, it's going to places like India, China, and this because the labor is cheaper. Things are cheaper, is going that way. But the infrastructure must be in place. That's where the political aspect of things come into place. The infrastructure to support that must come into play. And what do I mean by that? The young engineers coming out must have those relevant skill sets that are relevant to the economy, right? That can drive value, right? It's not just a degree. A degree is not good enough. It's what most corporations look at is how can you help me? What value can you add on to me? Do you have the skills, not the degree, there's a difference. Do you have the skill set that will help me? Degree is one thing, the skill set. So basically from the production of graduates that we have, they must have those skill sets, so that at the end of the day, the atmosphere must be there. The workforce must have those skill sets, all those work in hand, for people to look at Nigeria and say, wow, I believe the human capital is there, but the technical expertise, how we build people together, technical expertise, there might be a little bit shift in it, right? Because engineering as a whole is very, very dynamic. What I learned when I did my PhD today, to a lesser extent, is irrelevant. It's moved on, so I have to keep up with things, right? Like, for example, we're talking about CFD. Today, people are looking at using machine learning in CFD, using artificial neural networks in CFD. So things are dynamic, are changing. For us to be relevant, I myself, the nation as a whole, we must produce people that can contribute, to the larger economy. I look at it, the larger economy, in the sense that it's a global economy, the way we are, the way we are right now. It's a global economy. Let's say it's a waterfall. People will go to where they can have value, where it's cheapest. And I think Nigeria has that potential to tap into it. We have the workforce, we have the capabilities, just making sure the infrastructure is in place and the engineers we are training have those relevant skill sets. Take, for example, today, if people are doing numerical methods, it's good to do it on paper, but how does it apply? Use softwares that people will use in the industry, right, that are relevant to them. And I know some of those softwares, the challenge is that they're expensive, but now that gap has been bridged because there are open source alternatives now that are as competent as commercial based ones. So that's my take on things. That always remember, if there's anything you get out of this lecture as it relates to Nigeria, it's always remember it's value-based engineering. How can you add value to me as an organization? How can Nigeria add value to the global economy in this space, right, as a whole, right? That's what people will look at. And I don't believe it's whether you are developing or developer. I've interacted with people that are in similar scale with the state Nigeria is in, and part of it is because they have certain infrastructure in place, and then secondly is because some of their workforce, as they are being turned out, they have skill sets that are relevant to the economy they are in. I think that's my take on things. Hopefully I answered that question.
Thank you very much. Very elaborate. Finally, I just want to throw in this last one, which could also benefit Nigeria. I guess energy is an issue when you mention infrastructure instead of the skills. We also have the power, because most of these CFD programs are they run for some hours. You need to have steady power supply. And all that. Now, to provide energy for Nigeria, I don't know how much you've been involved with PCMs, phase change materials. Now, which basically one can use CFD, model them so that they can absorb energy or store energy and then release it when required. For example, we have, in terms of thermal fluid, we have huge sunshine, solar power. I know there is these solar panels and all that, everybody, but there's another dimension. We can build this into phase change material. So things that can store energy under heat and then release it when required. So are there soft CFD models you recommend for phase change material that can deal with that?
Yeah, I've not really looked into that. I'm sure there will be CFD models that are there for, you can use the general purpose CFD, but the level of customization that you might do, I've really not looked into that. But if you're going to look at the starting point, if you have the money and the resource and everything, I would say, okay, you can look at softwares like Fluent, you can look at StarCCM, Siemens StarCCM. If there's a financial constraints, you can start with OpenFOAM. It's free, but basically you have to put in your hours and your technical expertise into developing. And there might be solvers out there within the OpenFOAM context that have phase change already in there, and that's another approach. You can look at technical papers, but basically the development work needs to be in place. I'm not sure whether OpenFOAM has it, neither Fluent or StarCCM, but generally the generic CFD codes should be able to handle that. And but it's not going to be not only one tool will answer all problems. CFD is not the answer to all problems, definitely not. But you can use CFD in collaboration with other engineering tools to answer problems. That's basically the theme here. You can use hand calculation, you can use, but basically what the question is, what are you trying to answer? If you're looking at phase change model, is it the energy density problem? Is it what exactly are you trying to answer? Will determine what tool you want to use. For example, if you want to nail a nail to the wall, you use an hammer. You're not going to use something else. But if you're going to use, driving a screw, you're not going to use an hammer. So it depends on what you're trying to solve, and then as a whole, using all those tools to answer your problem. I'll give you a context. Like when I worked at Whirlpool, then they were trying to develop a heat pump dryer. Now, to develop a heat pump dryer then will involve a refrigerant cycle. We develop your thermodynamics with CFD, with the control systems, how you control, and it's a whole system as a whole. So you look at it from a system approach, and CFD is such a high fidelity model that if you're trying to simulate that whole drying cycle for like 45 minutes, it's not possible. So basically you use CFD for some part, get surrogate system model, plug it into a thermodynamic model that can run for longer to answer your problem. So it depends on what you want to answer. For example, what you're talking about might have to be a system level approach to things, right? There are some you use CFD, there are some you use what I call a system modeling approach to answer the problem. So
thank you very much.
Yeah.
Okay, I think that's all that we can take for now. Well exhausted. I'll thank you for all the answers. I'll pass on to Emmanuel.
Thank you very much, Engineer Sharp, for moderating that session. And very, very many thanks again to you, Dr. Bamiro, for this wonderful session. It's been really enriching for me personally, and I think for everyone who has been on here. We had over almost 100 people, and we still have a lot of numerical strength even at this moment as we rush against time. I think you probably have made the final remarks already, except if you have any other thing to add on. Okay, so
the only other thing I have to add on is that this is a playing field that Nigeria can play in. It aches me at heart at times when I collaborate with people, particularly from Asian countries, and I say, man, we can do this in Nigeria, but that kind of just say, man, we can do this in Nigeria. Guys are smart, guys are this, they can do this, they can do, but I believe, just like I mentioned, that infrastructure, that training needs to be in place, and some people that have the wherewithal and the power that be, put those infrastructure in place. I think the sky is the limit. And an example, it's the startup, I've forgotten the name in Nigeria now, that came up from Nigeria, that is valued at, is a fintech, billions of dollars, compared to places like Wema Bank and all those other banks that have been there, right? It shows you the power of a knowledge-based entrepreneurship economy, right? Everything, the way the economy of the world is going is knowledge value based, right? Not resource based. You have that at the back of your mind. So, so if we move towards that, there's countries that thrive just based on technical expertise and providing services. That's it. And nothing more. And that's my vision for Nigeria as a whole. If that value-based engineering, not just engineering, just entrepreneurs, and you see, just like that, knowledge-based, So that's my take on things. Yeah, thank you.
Thanks a lot. Thanks so much. I can see the passion that's coming with that. And I want to do something very unprepared right now. I would take the permission of my chairman. I think there are a couple of NSC chairmen in this meeting, and I think the executive secretary was also supposed to be around. We're expecting him. I don't know if he's around. I want to set up or to propose setting up a very small pre-committee, whatever it's called, to take this discussion further, if my chairman permits me, of 3, 4, 5 people, maybe chairmen of other branches who are present with our branch, and then with the speaker today. If you can just set up a meeting now for at any time later on in the week or later on in the month to just start up some discussion around this. Because the other time, Engineer Sharp also made a presentation similar to this one. He talked about this outsourcing issue and how Nigeria can leverage on the opportunities around there. And we had the Vice Chancellor of, I think, Landmark University, who was present on that day and was looking forward to how we can come in and collaborate with him and the university to see how these things can be set up. I think he's very much open to this kind of thinking, which is the forward thinking now, going away from degrees and how we can get applicable skills for engineering students and graduates to get into this kind of space. So, Mr. Chairman, so if you permit me, and Dr. Bamiro has some time, we can just set up a quasi committee now of 4, 5, 6, 7 people that can meet up later next week or sometime this month to get this kick-started. And then we can forward it to the national headquarters and take the discussions from there. Sorry if I'm breaking protocol right now, but I just want action to start up if it's possible. Chairman, sir.
Yes, I totally agree. This is what we need. This is one of the things, and the last discussion I had with Yinka, we almost for 3 hours. This is part of things we discussed. So for me, I think this is, we need to start. We'll do always have this mind of we'll do it and to do list. We need to start now. We need to start.
Yes.
We need to start something now. So without any doubt or without any, let's put the protocol aside. I totally agree with that. I think we need, In fact, I have with me here as well. It's my childhood friend and a family friend and someone that is very close to me. He's from the surveying industry. So he actually went to Nigeria to want to do similar thing because he is head of a department in his company in Ireland. Is here with me, Jerry Piala. Is in fact, I would love to invite him to. He is into surveying. He went to similar thing to establish that in Nigeria.
Awesome.
You know, so it's high time we need to collaborate and move these things forward. Yeah, let's go for it, please.
So if you don't mind, Mr. Chava, at the end of this session, if you and the speaker of today, Dr. Bamiro, please, if you don't mind, for some more minutes, and all NSC chairmen who are present, if you can just wait for some moment after the session ends, and then we can probably agree on some concrete time to meet and work on this, if that works for you. Thanks so much. So I'll just move on.
Yeah, sorry. I also want to recognize the head of Department of Mechanical Engineering, and you are our professor now, Dr. Ismail is here as well with us here as well. Please, because these are the people we need to make this kind of thing happen. We need the people in academics, we need people in industry as well.
Yes.
So, and also, sir, if you don't mind to wait, Professor Ismail, so we appreciate you, and and we don't mind if to collaborate with you as well. Thank you.
Great.
All right.
Hello, moderator. Sorry for interruption. Hello. Are you there?
Hello, sir.
Yeah. We have a university in Ibadan too, which is a state university. First Technical University Ibadan. So I am the head of Department of Biomedical and Electrical Electronics Engineering.
All right.
Such collaborations too, we are actually looking for, and I wouldn't know whether I can be part of.
Please, we are more than happy for you to join, please.
You are invited, sir.
Yes,
please. Thank you.
Thank you so much. Yes. So I'll just run through the announcements quickly. I think we are just at the nick of time. The first one we have here is from our sister branch, the NSC Manchester branch, and they are inviting us to their March general meeting and technical session. They will be exploring managing failures in energy systems. Are we masters or slaves of data? And Dr. Akilu Yunusa Kaltungo would be the speaker for that day. It's on Friday, the 26th of March, and it's starting by 5 p.m. UK time and 6 p.m. Nigerian time. The Zoom details are all available there. And next up is for us here at NSC Glasgow branch. We'll be having a general meeting on the 27th of March. 27th of March, Saturday, is our general meeting. So all members are welcome. Prospective members are also welcome. We're a very open branch. Happy to welcome you all in. It's beginning at 4 p.m. UK time. And we'll also be discussing the theme of this year's World Engineering Day, Engineering for a Healthy Planet, among other things we'll be looking at. These will be shared across our platforms, and feel free to distribute it generally to your contacts as well. And we have also our next webinar, which is the one for April, and they will be exploring Industry 4.0, application to energy transition and decarbonization. And our speaker, Ayo Ofi, I think is present at this meeting, will be addressing application of automation and AI to improving efficiencies, performance, and environmental impact in the energy sector. So this is playing in that league of data, AI, machine learning, and all of that, Industry 4.0. And the date is Saturday, 10th of April, 2021, starting at 5 p.m. I think at that time, the UK and the Nigerian time will be the same already. So we're looking at 5 p.m. British summer time, at same 5 p.m. in Nigeria. The Zoom details are also here, and these will be circulated across our platforms as well. We still have a minute or so for appreciation, so I'll just call on the secretary of the branch, Engineer Charles Okafor, to give a vote of thanks to appreciate our speaker and everyone for all your contributions and patience. Engineer Charles.
Thank you very much, Dr. Emmanuel. I think the vote of thanks has already been done by you because you have taken time to really appreciate Dr. Bamiro for this justice he has done to this very topic. And thank you very, very much. It is something that, we all need, and I'm happy with the level of, interaction. And obviously, you can see different players, university and the rest of them coming in to say, how do we move on from here? So we can't really begin to argue now that we are not heading somewhere. I think we will definitely get to where, everybody desires on this, and that is getting something out for the whole society. Once again, we do appreciate you, the time you've taken to put these articles together and to give us this wonderful presentation. And we sincerely do look forward to having you, giving us more presentation in the future. Also, for as many as are here, the head of department from different places, we do thank you for your time and for being part of this meeting today. Thank you very much, and thanks everybody. Over to you, Dr. Manuel.
Thank you very much. Thank you all for coming. Without you, there will be no program at all. So these are our social media contacts, all of our details. You can reach out to NSC Glasgow. We are very, very digital. We're very, very social. We're very, very welcoming. So reach out to us via email. You can see also the videos of all our webinars so far on our YouTube channel. This one as well will be uploaded on the YouTube channel. And I think some people were asking for the presentation slides and all that. It's going to be on YouTube, so you can have access to all of the detail, all of that from there. We're also on Twitter, we're on Facebook, and you can visit our website, which is wearing a very brand new, wonderful look right now, and reach out to us. We're very, very happy to collaborate with you. On this note, I want to say thank you all and have a wonderful time wherever you are. And please, all chairmen present, the HOD Dr. Adeaga and our chairman and and the speaker, please do hang on so we can have that discussion and have some direction with this passionate idea. Thank you once again, and bye-bye from us. Thanks.
Mr. Jerry Biala, can you also wait as well, please? You need to be part of this.
Okay, no worries. Thanks.
Sure, I think with the upload on video on YouTube, do we need to share the slides? People are asking for the slides to be emailed to them. I don't know if that